Hi, my name is Mohammed Rahman, aka Mo. This video is a presentation of my final project for Math 336/636. It's a combinatorics class at Queens College taught by Professor Christopher Hanusa. Before I begin, I want to briefly acknowledge that my in-class presentation of this project did not reflect my understanding of the material as well as I had hoped. And I'm grateful to Professor Hanusa for giving me the opportunity to present this work again in a clearer and more complete way through this video. My project explores a counting question inspired by Sudoku, and the question is, in how many ways can a 6 by 6 Sudoku grid with 2 by 3 subblocks be completed into a valid solution when additional symmetry constraints are imposed? Rather than trying to compute an exact total, my focus is to understand how imposing symmetry changes the structure of the solution space. So a standard 6 by 6 Sudoku has 282,009,600 valid solutions. However, knowing this total alone doesn't explain how the structure of the grid influences that count. The motivation for this project was to understand how structural symmetry reshapes the solution space. So, by imposing symmetric constraints, the problem becomes more structured and can then be analyzed using ideas from combinatorics and symmetry based reasoning. I work with a 6 by 6 Sudoku grid because, as advised by Professor Hanusa, it's the 6 by 6 grid at least is complex enough to be interesting in comparison, but still manageable in comparison to the standard 9 by 9 Sudoku grid. The Sudoku structure um, remains the same. Um, Once again, the grid size is 6 by 6. Each number appears exactly once per row, once per column, and once per 2 by 3 subblocks. Note that the symmetry constraints are added on top of all these rules, um, and all standard Sudoku conditions otherwise still apply. The first symmetry I studied is the vertical mirror symmetry, and before I eh, get into the nitty gritty of it, I'd like to explain the math behind it. And I'm gonna scroll down to get to the math. Um, I labeled the columns of the grid from 1 to 6. Um, the row and the column of a particular block is denoted as R and C. The vertical mirror symmetry is between the columns 3 and 4, since uh, this grid has an even number of columns. Um, so this vertical mirror symmetry can be written as a function of sigma of RC, and the sigma of RC equals R f of C. And the reason why is it so is because in a vertical mirror symmetry, the rows stays the same, but the columns change where the columns uh, the of one side of the symmetry is a reflection of the other side. So um, if, for the function of sigma of RC, C can be denoted as a function of f of C for some function in the columns. Um, this can then be used for the pairings of column um, such for the pairings of columns 1 that can be paired with 6, columns 2 can be paired with 5, columns 3 can then be paired with 4. And this pairing then ends up satisfying the following equation: C plus f of C equals 7. Um, the reason why it is 7 is because if you add the column with the reflection of the column of C plus f of C, 1 plus 6 equals 7, 2 plus 5 equals 7, 3 plus 4 equals 7. So therefore, C plus f of C equals 7. If you solve for f of C equals 7 minus C. Um, you can verify that this function can be a symmetry. It maps the columns correctly. For example, for f of 1 for the equals 6, column 1 maps to column 6. F of 2 equals 5, f of 3 equals 4, and so on and so forth. So therefore, the left and right columns swap as expected. It also can be written as a reflection on itself. So the function of f of c can be written as 7 minus 7 of c, and that f of c equals 7 minus 7 of c, and that equals c. So if you apply the symmetry twice, it returns the original cell, which is c. So in the end, if you put it all together, sigma of rc can be written as r stays the same, so sigma of rc is r, c ends up becoming 7 minus c. There are 36 cells in total, with the vertical symmetry in between column 3 and 4. There are now 18 symmetric pairs on either side, and later we will discuss that this 18 symmetric pairs can be considered as 18 degrees of freedom, but we'll get to that later. The next symmetry I studied is the main diagonal symmetry. So in this case, um, each cell RC is paired with C of R, um, to the main diagonal line. Now, unlike the vertical symmetry, this diagonal symmetry has fixed points. For example, um, if you look at the cells 1 1, it maps to itself. So 1 1 remains as 1 1, 2 2 remains as 2 2. The cells off the diagonal form symmetric pairs of 2 5 that maps to 5 2. So RC maps to CR in that case. Um, so with these 6 diagonal cells that remain fixed, you out of the 36 cells here, you remain with 30 off diagonal cells with 15 symmetric pairs on either side. And uh, if you add the symmetric pairs with the diagonal fixed pairs, 15 over 6 in total, you get 21 degrees of freedom for the main diagonal symmetry. So in conclusion, um, this out of the 36 independent cells of the 6 by 6 Sudoku, with the vertical mirror cells, this reduces to 18 symmetric pairs, therefore 18 degrees of freedom. With main diagonal symmetry, there are 6 fixed cells with 15 symmetric pairs, and that gives you 21 degrees of freedom. So symmetry alone significantly reduces the number of independent choices. Therefore, um, symmetry alone significantly reduces the number of independent choices, even before Sudoku spaces are applied, even before applying row and column or block constraints, as per se. So, in conclusion, this project shows that the symmetry does more than just add structure to Sudoku. Um, it transforms a large enumeration problem into a structural combinatorial one where different symmetries reduce freedom in a different way. For the next step, I would like to explore different computational methods to enumerate different symmetric solutions and investigate how combining these multiple symmetries further restricts or reshapes the solution space. I would like to once again thank Professor Hanusa for his time in class throughout the fall semester and for the opportunity to revisit and present this project more clearly here. That's all. Thank you for watching.